Okay. Hello, everyone. So this is a paper that we came across while we were writing our project report and like our paper. But this was one of the few interesting ones that I kept for like reading later. So I came back to it this week because it had some interesting ideas that could explain some of the empirical observations that we saw in our work, and hopefully it could explain some things that you have seen as well. So this was published in 2019 in ICML, and it's a heavily like theoretical paper, but it describes how neural networks are learning, and it tries to describe what happens in neural networks, especially focusing on spectral biases. So I'll get on that as we go on. So the question that they motivate themselves is that they observed by 2019 that there are huge models, deep learning models, that have shown empirical success, especially on real world data, like reconstructing natural looking images and things like that. But the models are very large. And on the other hand, in a traditional sense, we know that when we normally over parameterize models, it tends to overfit and generalization becomes a problem. And if you like, the simple example is if we like parameterize maybe 10 parameters instead of a 2-variable quadratic function, we normally overfit into a very weird polynomial, and that's the problem. But how do these two match? So if the real world images are in some dimensionality, why do large models work? So this is their motivating question, and they are special interest area in these types of papers and their reference papers is that they are trying to find what are the implicit regularizers, or with the choice of some nonlinear activations or some type of deep learning layers, what are we implicitly giving to our model so that they work in the real world. So that's what they try to analyze. And what they come up with is this quote unquote bias towards a low complexity solution. So a low complexity solution in a general sense means it's not parameterized in large parameter space, but in this paper specifically, what they look for is low frequencies. And in the paper, they say that they change the question slightly, and they suggest that when you're learning in a deep learning setting like gradient descent, what they observe and what they theoretically and practically both try to show is that the first few iterations always they observe that it's easily converging to a low frequency solution, and that to get to fine tune a model into high frequencies is the hard part when you're going in traditional sense. And that's what they are trying to show theoretically as well as in experiments. And this term called a spectral bias is what they introduce. Yes.
I asked a question. Yeah, so these are like, we are explicitly talking about CNNs, or like this is in general over parameterized models?
The introduction and like the motivations are in general over parameterized models, but in the paper they focus on DNNs, not even CNNs, just a deep neural network layer with ReLU functions.
Well, what does a deep neural network layer mean?
WX plus B type weight matrix with a bias, with a like additional bias, WX plus B term, and then a nonlinear activation.
Okay, so basically what they're doing, it's like a fully connected model.
Yeah. Yes.
Okay. Okay.
And
Sounds.
yeah. So this term called a spectral bias, this was like coined by these authors, and then this was again referenced later by the Nerf paper and like related work which had cited this as a potential problem is that the tendency of a model, in this case, what they are showing is for a fully connected layer with a ReLU activation, is that it tends to learn a low frequency solution, even though the target function has some high frequency components, and they run different experiments with like synthetic data as well as MNIST data to show that even though the high frequency components are high, so if they change the coefficient values of the high frequencies in their synthetic data, or they change the ground truth, even then the first learning iterations or the first few epochs always goes into the low frequency solution. So that's what they show. And like additionally, what they show is a sort of a delicate situation when you're learning the high frequencies. So by delicate, what I mean is they say that learning high frequency parts of the model is relatively harder. And once you learn it, it's more fragile to noise. So they just perturb the parameters and see the performance of the models, and compared to a low frequency trained model, they show that the model is very sensitive and the accuracy drops very fast when a model is trained to a high frequency, when trained to capture high frequency information. And like these three are the main contributions of the paper. They theoretically like comprehensively cover the ReLU part, not other types of models like CNNs, but like their argument is in a general sense, but here in the paper they cover for ReLU networks, and they formalize the concept of a Fourier space when input is passed through a ReLU network. So I'll show that in the next slide. And after they formalize a thing called a Fourier space when an input is gone through a ReLU network, they show that the components, once you have a Fourier space, the high frequency components are harder to learn, and the low frequency components are easier to learn. And then lastly, they show that even like in machine learning practice, we know that sometimes we can manipulate the inputs, like in traditional sense, we transform the features. So it's more or less like alchemy, like we do different transformations and just stick to what works. But here they like try to fit that into this model as well. What they say is when you have a high frequency information, like a model fitted for high frequencies, you can do some transformations for the input so that your simple like low frequency inputs are transformed into a quote unquote manifold, and then that model will fit better to a manifold. So again, that's a bit mathematical, but I think the first 2 points are the major things that we could gain insights for our work. And like to understand first is they just establish the concept of the Fourier space in the ReLU. So first they motivate why they select ReLU. So what they tell is like we know the like power of deep learning comes from that universal functional approximating story, and they say that even the ReLU function works both ways. Like you can approximate any piecewise linear function with a ReLU function, and any piecewise linear function can be broken down into its ReLU components. So they say that first, and then they describe the parameters or the input space in terms of this figure on the right called a polytope. So a polytope, I searched and found that it's like a convex shaped 3D space where the bounds are linearly like linear regions patched together to form a higher, like a higher dimensional volume. So it's like a polygon, but it's a bit general than that. So they are working in these polytope spaces, and they say is that first that you can approximate functions of where the domain is restricted in some way, like this polytope. They say that the ReLU function is a good function as a choice for approximating piecewise continuous functions. And then they go on to the Fourier spectrum. Again, the maths is a bit convoluted, but here the K term in this lemma 1 is what we are familiar with as omega, or the frequency. And it's also like a high dimensional input. And there is always a Fourier component corresponding to each K term. So in the bottom, they have like shown that integral over P is our polytope. And they go over that integral e to the power minus I kx, and they take that integral over all that indicated a function is over all defined areas of the polytope where the function is defined, and they have the weight matrix and some other terms, normalizing factors, to get a decomposition for the Fourier transform. And they formalize this, and like without thinking too much about the details, like even the like after the first equation, the second and third equation requires a lot of I think mathematics to understand. But what mattered to me at least was the conclusion that they got was, once they decompose this Fourier f dash k, they decomposed into like a sum of different k's, and then each k has a decaying component. So there's a denominator in this term. So in the equation 6, there is a denominator for each part of the Fourier component. So what they say is this is a decaying thing, and when you're in high dimensions, it's easily decaying, and it's not isotropic, it's anisotropic. That means in some directions of your higher dimensions, these Fourier components are decaying, and in other directions, it's decaying in other, like in a non-uniform way. So they are theoretically analyzing how these Fourier components decay, and then they go on to experiments to show like the easiest thing is to learn the smaller Fourier components. So what they are, the connection between this decaying story and the like motivation I mentioned earlier is that when you have highly decaying Fourier components, what I think the connection is that the model finds it harder to fit, because in high dimensions, it's a very insignificant part of information. So it's like the Fourier coefficient, when it's very small, and it's in theoretical sense, it's shown to be small, but in a practical sense also, it's very hard to fit. But the easiest thing for the model to find is the relatively higher Fourier components, which are the low frequency ones. And like the first set of experiments that they show is synthetic data. So
so can you go back to a few slides? So here, when you refer the frequency, is it like really the Fourier transform, or is it, are they like using it as a loosely sense? So equation 4 comes from Fourier transform. Is there anything to do with the Fourier transform, or is it just the structure of the Fourier transform?
No, it's the structure of the Fourier transform, because they use that structure of integral over e to the power j story, but it's not the exact. There's no exact correspondence to what we are familiar. Partly because the input is like in dimensions. So the space they are talking about is like a So we know Fourier transform in 1D, Fourier transform in 2D for images. In that sense, they are talking about a Fourier transform in higher dimensions, which is K, and that K is not anything that we are familiar with, like a discrete or continuous frequency. It's just a vector.
But that equation, like, I don't know, this 1pk, like one below the equation 4.
Yeah.
That's the Fourier transform, right?
Yes, it's like selecting possible regions of our input space P and then applying Fourier transform over it.
Okay, I see. Mm-hmm.
And like because they have used these like weight terms, like because of the like linear layers and the normalizing factors like k squared, I'm not sure whether it's from my side, I think that it's not directly the Fourier transform equation, just has that shape.
I see. Okay.
And in this first set of experiments, like I think we have all like seen this pattern, but this paper like theoretically validates these observations.
That's one more thing. Can you go back to the equation 4? So basically the E exponential like minus ij, like that is there, right, in the equation?
Yes.
The moment you put it, like, you actually get the real frequencies, right? Because you have the sines and cosines inside.
Yeah.
Okay.
So these types of curves I have seen, and I think most of you have seen, like in the first few iterations, we always, it's not a big surprise that this happens, but these people argue why this happens. So their justification or their claim is that this is due to this thing called spectral bias, where the model easily finds the low frequencies, and it's up to us to decide, like in previous like machine learning practice, what we do is we stop the iterations before like some sort of overfitting happens. But in this case, the first set of experiments, they give design functions with different frequencies, like in this set of kappa, they have different frequencies k1, k2, and then they go on to design functions with different frequencies, and then they for each frequency they train it. They train the model starting from a random initialization, and then they see how the first few iterations the prediction goes, and then the first 1,000, after the first 10,000, and after the first 80,000. And
what's the loss here?
MSE, just mean square. And then the model would be, they have different frequency ground truths, and inputs are 0 to 1, and then the model is a fully connected layer with ReLU activations, and then the loss is mean square. And this is like not very surprising, but they are like how they analyze it is how they give insights. So this figure sort of is interesting, where on the left two images they give for their ground truths, they have designed in a way that equal amplitudes of each frequency is in the ground. So for low frequency, the component and the high frequency component have same amplitudes in the ground. And on the right chart, the amplitudes of the ground truths are different, where they have focused or they have prioritized with high amplitudes the higher frequency ones. But the charts look almost the same. So on first glance, it's as if there's no difference in how the model learns the things, even though the ground truths are different. Some have higher frequencies in the ground truths. So if we just focus on this left side things like the blue, green charts, is what they do is they compare on the y-axis what happens after each iteration, and on the x-axis it is the frequency axis. So what they do is they give they compare the ground truth prediction with the input with the model prediction, and they normalize it to 0, 1. So what they see is the low frequencies like 5 and 10 after 10,000, 20, even before 10,000 iterations, the prediction achieves the ground truth values with low frequency. But for high frequency, it takes a lot of time to get there. It gets there, but it gets there after 30,000, 40,000, maybe even 60,000 iterations. But that nature is still, yeah.
What is that graph? So what's the color? How do you read the color?
All right. So the lighter green means more close to the ground truth, like actual data. So the prediction divided by ground truth is 1.
Prediction divide by ground truth. So basically this white means it is better, right?
Yes, white means it's better.
The dark means it's bad. Okay.
It's way off. Yes, yes.
So it's not the difference, it's the ratio, something like that.
Ratio, yes. And so, and that nature is there even if the ground truths have ground truth data is trained with higher frequency ones, for like with high component, high coefficients, or if the synthetic data has equal coefficients for low frequency and high frequency. So the behavior of the training has not changed. That's what they show here. And in the like training curves that they have shown, they have this is the training curves on the right hand side of each part A and B is for each layer, they have shown the magnitude or the norms of the weights in each layer. So that in a sense is like not that important to the claim. What they show is like with training, the model weights start to increase. So this is without any regularizing loss or anything. So the model weights start to increase and they try to correlate that with learning higher frequencies. So when each layer, the model weights, so the W's of each layer in the connected network with ReLUs, when the norms of these layers increase, they say that it correlates with learning higher frequencies. So that's this set of experiments with synthetic data. And then, yeah.
They repeated these experiments for like L1 loss or something different, not L2.
I don't think they have repeated for different loss functions.
Because if you L2 loss, like you have this property, right, where like it tried to first estimate like the average. That's the easiest way to minimize the L2.
Yeah, yes.
And you can think about low frequencies as basically like regional averages, right?
Yes. So that I think the question is like, is this the property of the loss function, or is this the property of the way we are learning, like the model?
Yeah, exactly.
Yeah, I didn't come across any mention about like different loss functions. Maybe I should check the ablation or something.
Yeah, maybe check that, and if it is yeah, if it has not been investigated, it might be interesting to see, like because the experiments are simple, right? The models are simple, and all the data sets are, I think, simulated, right?
Yes, simulated data sets, and one is MNIST. So simple.
That might be interesting to see, like repeat the experiment with a different loss and see what happens.
Yeah. And the second experiment is with the perturbing, like still synthetic data, but what they do is once you have a trained model, they change the weights slightly. So after convergence to this theta star, what they do is they randomly perturb the weights with a small delta theta hat, and then get a prediction of the perturbed model, and then compare it with the original like trained model and see how much that differs. So again, the ratio is taken, and the whiter the color, that means better. That means there is not much of a difference in ratio. Like the ratio is almost 1 when you have the originally trained one, and when the weights are slightly changed. So for the parts that are low frequency, or the models that are predicting low frequency information, it's relatively like it's more stable. And the models that are for the higher frequencies, with a slight change in the model weights, the predictions go like differ very much, and the ratio between them is, the ratio of the magnitudes between them is almost 0 in some cases. So that's what they show here. And that is what I mentioned, as the models become more and more fragile as you try to fit higher and higher frequencies into the model. So this is what we saw in our project, because we were trying to like improve like PSNR and SSIM of our reconstruction models by like fitting higher frequencies, and like that was our project. And then what we saw was even the slightest change somewhere made results go very like unpredictable in the change in the model, but not change in the data, change in the model. So the model is sort of more fragile, what we saw empirically, and this paper like tells that when the model is trained to fit for higher frequencies. And like in the bottom, like what I highlighted here is that parameters are finely tuned to work together, and the parameters that are tuned occupies a very small portion of the large parameter space, and a small change in that again like disrupts the whole fine tuning. So it's intuitive, but I haven't reported the maths here. The paper, they like theoretically show that this happens. And then they move on to real data, means MNIST, where they repeat that same types of experiments, where they run it for different amplitudes of frequencies. And so if we just focus on, let's say, so in real world, yeah, in this one, they have added different noise frequencies. So by noise frequencies, what they have done is they have not added like things like Gaussian noise. What they have done is also like a synthetic type of noise, where they add sinusoidal functions to the ground truth with different weights, and each sinusoidal function has a different weighted term for the frequency component. And then they add that synthetically generated noise to the ground truth image, and then they create a data set of the original image and the noised image, and then they train on these noised images and see how the performance works, how the model tries to learn the underlying ground truths and stuff. So what they first see is that when the frequencies, like when you're going for frequencies from like say 0.1 region to frequency magnitude 1. So this K is the magnitude of the frequency vector. And when that is increasing, there is this dip happening. So this dip, what they interpret it as the first, within the first few iterations of the training, all these curves are almost together. And what they say is when going for higher frequencies, it doesn't matter in the first few iterations. For the model, it's almost together, and after some time, the changes are apparent for different magnitudes of the coefficients. So these different values of different curves are different amplitudes of the training, let's say this beta. That is the different amplitudes of the noise term, and that becomes significant only after some time of training. So, and then again here they have, for two different instances of the amplitude, they have then flipped the parameters and then run for different, more resolution in the frequency. So different models with different frequencies. Again, there is a dip happening, and within the first few learning iterations, these models with training for 0.25, 0.3, 0.5, they do show, especially for the higher frequencies like 0.5, 0.3, and 0.25, those models are always almost overlapping in these first few things. So that's what they show, and they are.
I'm a little confused with these graphs. So they are MSE loss for a certain frequency?
Yes, so there are two things happening, two parameters. One is the amplitude of the noise term, which is K. And then there is another parameter, which is the which is beta, sorry. And then there is another beta, which is the amplitude of the noise. And then there's a frequency K. So these two are the two parameters. In the first graph A and B, they are comparing different betas for two Ks. And then here they are comparing different Ks for two betas.
But the loss is for the all the frequencies, or the loss is plotted for some frequency? Because the loss goes down and comes back up, right? So that's
yeah. So in this curve, I think now in both curves, the loss is for separate frequencies.
So what you're saying is, like, if you look at the loss, if you decompose the loss into different frequencies, and then for some frequencies, like the model first becomes better and then like it becomes worse while
Yes.
you train.
Yes. And the degree of getting worse is like more worse for higher frequencies. So the dip is stronger for higher frequencies.
So it becomes like, okay. Mm-hmm.
And like in this description, in this gist, they say low frequency noise affects the network more than high frequency, and that this story of the dip happening early in the training. And this is, they'll argue this is all again connected to that claim where the network readily fits low frequencies, but the fitting for higher frequencies happens later. So this experiment is showing when the higher frequencies fitting happens and how the loss function changes with time, with training iterations.
So let me see if I understood this right. So basically what they did is, like, they have the natural, these are done for like real data, right? So for real data, what they did is, like, they just put some sinusoidals inside the real data.
Yes.
So you can observe them. And those are the noise.
Yes.
So they say, like, and the model first passes them, right? If you look at it in this way, because if the loss is low, Oh, the loss is calculated without those noise terms or with these noise terms?
Loss is calculated with the prediction from the noise terms compared to the original ones.
Original one, which does not have these noise terms.
Yeah.
So if you say like the loss is low, that means like the model gotten rid of those added frequencies.
Yeah.
Okay, so if I think about this, now what I would expect is to happen if the model first learns to fit the lower frequencies first, then it should also probably pass those noise terms in the lower frequencies first.
Yeah.
So is that the case we are seeing? So for low frequency noise, you will see the MSC loss higher at the beginning. Like the dip will be lower for low frequencies. Is that right or not?
The dip is lower for low frequencies. Yes.
Okay. And the dip should be higher for high frequencies because the model get rid of these frequencies anyways at first.
Yes.
Okay, well, what is the model trained to do here? It's just to
It's just to predict the ground truth.
It's to predict the ground truth. Predict the ground truth means like this is a classification model or for the MNIST, or is it like a regression model? What is it?
I think it's just an MSE loss of the prediction versus the ground truth. So they haven't trained it for a task like that. It's just comparing the losses.
But what is the prediction?
Prediction is this to the target, which is the combined image, like the original with the noise.
Is the target is the original with the noise?
Yes.
So then it is a different law. So it is trying to predict the noise as a.
Yeah, but in the first iterations, it's insensitive to the high frequencies.
Okay, yeah. I don't fully understand this experiment, but like let's move on. I can look at it later.
And so what they conclude after this experiment is that even in their synthetic data and after like their non-synthetic data trainings, that their coined term of spectral bias, which is the deep learning models easily learning the low frequencies exist, and especially clearly seen when it's in high dimensions. And as an additional thing, what they show is they do a transformation to the input. So in this experiment, what they do is they take an input which is normalized. Let's say this Z is for the original input, let's say an image, and then they do a transformation which includes some frequency information like cosines and sines. But what they do is they do a transformation to take the inputs into a manifold. What they say is that is called a manifold, and that shape is this rotating petal-like structure what they have shown with dots. So what they have transformed the inputs into this space of a weird, not weird, like a pattern space which is shown in these dots. And so the ground truth for each input. So in this right-hand side image, it's a binary classification task, I think. And for each point in this image, it's either red or blue. So the input space is the all possible input space is shown here in the background, and in the dots they have shown the points that are in the manifold. So it's a low dimensional manifold inside the larger input space. And what they say is, after you transform the inputs into this manifold, it's almost a perfect prediction. So the dots which are red colored are the points in the manifold that are predicting red. And the ground truth is in the background, which is also red. That means it's a correct prediction. And the dots in the manifold which are blue are predicting blue, and the background is also blue. That means the prediction is correct. But when running two different instances, like once you train a model and then you randomly initialize it again and then again train another model, what they see is that the predictions change for the task, but the points on the manifold always predict correctly. So if you look at the same point on, let's say I look at this particular petal and that same petal here, the predictions on the manifold have not changed. So these three blue points are still here predicting blue, and then the next two red dots are again predicting red. Like that, the predictions in the manifold have not changed, but the predictions for the other parts have changed dramatically. So what they say is, that means the model has learned something of low frequency when the input is now in a manifold. So when the input has been incorporated with some frequency and has a predefined mapping like this, the fitted model is now sort of stable. It's not showing that property where once you change it a bit, change the model a bit, the predictions are going, the perturbations, the sensitivity has reduced by changing the input data so that it's now deterministically in a manifold. So that's what they like additionally show, like what can you do with it. So when there's high frequency information to be learned, it's better to incorporate some structure into the input so that the model's the learning part has to only deal with something of low frequency, and the input transformation that we do deals with whatever the high frequency that should be captured for the underlying function. So that is the last experiment. Yes. This is like an additional thing that they show as to what can you do with this knowledge. Like if you see a model which is training sensitive to high frequency trainings, you can change you can use a transformation so that your data is now, the input data is now having some structure, and within that low dimensional manifold structure, the learning is more stable than if you just gave it all the possible images to train. And yeah, so this is again the same experiment with different varying degrees of that transformation. So earlier there is a transformation happening with this capital L as a parameter. So this transformation L, the transformation gamma is depending on this L parameter. It is again corresponding to a frequency. And once you have a transformation, different degrees of that transformation, for L equals 0, L equals 4, 10, and 16, that difference between the model, from the model side of things, like the difference between the low frequencies and the high frequencies, that fades out when the input inputs are transformed in a higher and higher frequency. So when the inputs are transformed using higher and higher frequencies to give it a predefined structure, the difference between the models training for lower frequencies compared to higher frequencies is gone, and after like 10,000 iterations, even the high frequency predictions are relatively okay compared to the low frequency predictions. So their gist is that some manifold makes the network learn better and easier than in high frequencies than others. So what they have like in essence showed is they have shown some transformation to work for the inputs that enables the model to learn higher frequencies better. And in summary, they again like show what they have done. They have like mathematically talked about the ReLU networks and analyzed it in a Fourier sense. And then they have shown the decay of the components of higher frequencies. And then practically they have shown that there is a bias towards low frequencies in fitting. And then additionally, they have shown that even if you have a model like architecture that is sensitive to this bias story, you can reduce that effect and you can use some predefined transforms so that your inputs are now in a structured manifold and the model is now able to learn it better. And they have said that future work on things like analyzing things in this Fourier space and how to treat different frequencies separately is promising. And they have like ended it there for their work. And I didn't check the ablations to see whether they have repeated it for other losses. I think I will check it.
Great. So when was this paper published?
2019.
2019. So it's a few years ago, right? So, so are there any like follow-up work on this exact direction, not just using the conclusions of this study?
Exact directions. I think people have like come up with architectures based on the conclusions, like how to mitigate the low frequency bias and things like that. But I don't think I haven't searched it actually for direct extensions of this.
See, how many citations does it paper has? Must be many.
Yeah, let me check. $650, 638 on Google Scholar.
So that's probably still doable. Maybe like you can look up citations. Definitely, it's an interesting paper, and it might be interesting to see like what more they have done on top of this, since it's been a few years.
Yes.
Yeah. Any other questions? All right, I guess if there are no questions, like maybe we can wrap up and thank Tharindu